Thanks, László, that you found your time in this busy.
It was not easy. It was not easy.
Okay, thanks. Well, if you would be here, you could get a bottle of wine or a beer as as a reward. But unfortunately, we have to do it this way. So I will then turn off the microphone and the video so you can start to speak and take your time, and then we will then discuss the questions.
Okay. So can I start?
Take your time is not a good formulation.
It's not a good formulation. Nobody is saying that take your time is not a good formulation. So you have 1.5 hours.
Okay.
Bit less. 1 hour 20 minutes or something like that.
20 minutes. Okay. We will see. As you know, or actually many who know me know that I'm quite a lazy speaker. So it might easily happen that I will take 1.5 hours, but in spite that I just have about 35 slides. Never mind. So thanks for the introduction. So I'm, whoever doesn't know me, I'm László Szunyogh from Budapest. I'm working at the Technical University of Budapest, officially Budapest University of Technology and Economics in Budapest, Hungary. And I had the luck, the very good luck, to be one of the founder of the Screened KKR method, about which I want to give this talk. And before I forget, I don't think I will forget, but how to page down? Sorry, I cannot switch to the second slide. Okay, now I switched. So I immediately introduced the other founders, so to say, my good old co-worker Balázs Újfalusi, who will be actually the next speaker. Then Peter Weinberger, who hosted us in Vienna for many years, and in particular at the advent of the Screened KKR, and actually then two honorable colleagues from Jülich, Peter Dederiks and Rudolf Zeller. I can see that Rudi is among the audience. If R. Zeller is Rudi, I think so. Those two guys helped us actually, I would say, to understand what we are doing with Balázs when we started to work with Screened KKR. So let me first tell you that I prepared quite a technical talk. So because it's my understanding was that it's a summer school, and as a university teacher,
recording in progress.
Sorry. So sorry for this interruption. I switched off my mobile. So I just was telling you that this will be quite a technical talk, because I thought that it's basically for young people who probably doesn't know the method in details, and therefore the most part of my talk will be about technicalities and about the formal theory, and then I switch to the application, in particular to layered systems. And I'm sorry about the Jülich guys that I will just have one slide about the KKR Nano program, which also, at least in part, also uses the Screened KKR, the facilities provided by the Screened KKR. So these all mean that experienced guys, senior guys, can go for a beer, another beer, and I just hope that for younger, less experienced guys, this talk will be not so boring. I selected some if I'm at the content, so I selected very few applications, practically applications from the far future, not recent applications, but probably those which are traditionally most related to the foundation of the and early applications of Screened KKR. Fine. So as I said, I will start with a very elementary introduction. And I think that in the past two days you have heard quite some talks about the multiple scattering Green's function techniques. So therefore, I will just introduce the quantities I want to speak about and discuss some of the basics of the multiple scattering theory without any special explanation. Just stop me if you don't understand something and you think I have to make more explanation. So in particular, I will introduce the theory in a non-relativistic spinless framework because this is the simplest one, and the screening, the idea of screening is related to the so to say to the empty space where it is basically not relevant whether we deal with a non-relativistic or relativistic theory. Probably you will see what I mean, and I will just add 2 slides to a possible extension to a relativistic theory. So then let me start right with the formula of the Green's function. What you might have learned 2 days ago from either from Didier or from Hubert, who were speaking about the electronic structure application of multiple scattering theory. So here in this formula, sorry, the window for the zoom covers a part of my screen. So okay, I try to remove it, and therefore I cannot see a part of my screen. Okay, now it's better. So within this, so basically we have 2 kind of, probably more, but traditionally 2 kind of different formalism, but equivalent. So in the meaning, in the essence, equivalent formalism of the Green's function. One is with the so-called R and H functions, and the so-called structural Green's function matrix. The other one, which is used by us mostly with the scattering path operator and the Z type and the J type scattering solutions. Here you can see the normalization of these functions beyond the muffin tin, or in the zero potential, or a bit more exactly in the zero potential space. And later on, I will use when I will deal with the Green's function itself. I will use a column vector formula of these functions. So this applies also for the Z functions and the H functions. Again, I'm a little bit okay. Now I could minimize the zoom window. Sorry for that. Okay, so these are simply nothing but a row vector, so that all these functions with the angular momentum indices. I hope that you know what are these capital L in a non-relativistic theory, it is just the angular momentum quantum numbers, the composite angular momentum quantum numbers, LM. All right, and then you can just write these scattering solutions as in a row vector, and this is labeled by these slanted letters. All right, so R and C are the regular, and H and J are the irregular solutions. Scattering solutions. So this is just a very brief introduction, but the main quantities here, or for us at least, the more important quantities are these matrices, how they come about. This we can start with the free space Green's function, which has this well-known form, and for which we see, and I will come back to this point later on. For positive energies, that means in the region of the continuum spectrum, it is an oscillating function decaying with 1 over r. However, in out of the continuum, for the negative energy, it is an exponentially decaying function, and this will be more or less the point in the Screened KKR. Let me put forward. But now I just wrote this formula for the reason that to note that we can expand this free space Green's function on the same side when n, so the lattice points or the reference point of the coordinate system is the same, then as a kind of single side expansion in terms of the J and Hankel functions, and when n and m are different, that means the center of the expansion of the Bessel functions is different. Then we have these expansion coefficients, actually, which we call free space structure constants, and the real space expression, which you should know very well, I hope, from the former talks, has this form, and already from the original form of the free space Green's function, but also knowing the asymptotic form of the Hankel functions, we can immediately state that those free space structure constants are long range. That means in terms of the magnitude of this R vector, they decay very slowly, practically with 1 over R. And this will be a kind of problem if we want to deal with low dimensional systems. Now, these are the well-known. So this is the way how the matrices come to the formalism of the multiple scattering theory. So we have actually matrices with respect to the side indices, and then denote lattice sides, or simple. So it can be ordered or disordered lattice, no matter, of course, and LL prime are the, as I mentioned already, the angular momentum indices. So basically, these are what we call, or at least Peter Weinberger called it, always supermatrices. This is what we can take over this notation, and then what I don't want to speak too much about. This is the single side scattering formalism, or but also on the previous slide you have seen that they have to do with the scattering solutions. They are by definition diagonal in the side indices, whereas the G naught free space structure constants are by definition off diagonal, even for the the like sides, those are vanishing by definition, actually, because of this formula. So those are the basic matrices we deal with in multiple scattering formalism, and then we can define the so-called structural Green's function matrix, which I will abbreviate with SGF in the following, and this is related to the G naught and T matrices like this. This is a kind of dressed propagator, if I might say, without going into the very details of the mathematical foundation of multiple scattering. I let it to Didier and Hubert. And the scattering, the so-called scattering path operator or matrix of the scattering path operator is defined like this, and this is the formula which we like very much, because it treats separately the single side scattering, so what is really material specific. Of course, the structure is material specific too, but this is what is related to the scattering, and this is what is related to the structure, and this is very convenient in many applications of multiple scattering, and I just hope that I don't have to go into more details to explain these quantities, right? So still introduction, and then if we use the Neumann series of these expressions, then we get actually a kind of infinite series. What you can see here, and this is what tells us that this SGF, the structural Green's function matrix, is actually a dressed propagator, and here you can see, this is what how I always teach my students, that from the second term you can pull out from each term G naught to the right, and also T to the right, and what remains is G naught plus G naught T G naught, and so on and so forth, which is exactly the original SGF. So you can get a Dyson equation like this, but you can safely revert the order of G naught and G, and this is the same for the SPO. That means the scattering path operator matrix, which can be understood as a dressed T matrix or scattering matrix, and these exactly in the same way you can easily prove that these equations, these two equations hold true, and from these two formulas, in particular from the infinite series, you can also see that now, for example, sorry for the tutorial talk again. If you pull out from the second term G naught from the left and right, what remains in the parentheses is T G naught T, and so on and so forth, which is exactly the tau matrix, and immediately gives us the relationship between the structure of Green's function matrix and the SPO matrix, and vice versa. From this expression, you can immediately see that pulling out T to the left and right, what remains inside from the second term is G, and this is what we will make use later on when we want to find the necessary equations and formulas for the screened KKR. Right. Now we know everything, or more or less everything, about the basics of KKR, and then we want to know how to use it. In particular, how to calculate either the tau matrix or the G matrix. For example, from these equations, how to solve these equations actually in 3-dimension. In case of 3-dimensional periodicity, translational periodicity, it is quite simple because you can use the 3-dimensional lattice Fourier transform for the free structure constants, and you can suppose, but you can even easily prove that of course a similar lattice Fourier transform holds true for the tau matrix, for the SPO matrix, and then it is just a little algebra, elementary solid state physics. I will show an example later on to show that the original equation, fundamental equation for the SPO matrix survives in K space, or factorizes actually for each of the K components, and then you can see that once you can calculate the G naught, the K matrix, which is, for example, which can be learned from the famous seminal paper of Hammond-Stegall in terms of an Ewald sum, then all you have to do is just a matrix inversion in angular momentum space, which means that here we have small matrices. It's computationally, numerically, it's an easy task to do. Of course, the quite more evolved part of the calculation is how to take into account all the K vectors, so how to sample the K vectors and how to perform the K integration. But I don't want to go into details. I'm absolutely not expert in bulk calculations. So this is for me, so to say, a separate business. We have a bulk code actually. So I just 2 years ago with my postdoc András Deák, we programmed a bulk code. This is just for the colleagues. An announcement. That's right. And then of course, once we get the tau matrix in K space, then either we get this is a different part of the theory, but one can easily prove that the poles of the tau matrix or the zeros of the inverse tau matrix provide the dispersion relation, so you can easily produce the very nice spaghettis, so the band structure in K space, or integrating the tau matrix in the Brillouin zone, you get the real space representation of the, in this case, the side diagonal scattering path operator, from which you can calculate the density of states, densities, charges, moments, and whatever you can perform self-consistent calculations. And it is quite easy to say, probably not that easy to perform. You can do the bulk calculations. So at least theoretically, there is no problem with the three-dimensional with the case of three-dimensional translation and periodicity. Now, what about the two-dimensional case? So here I should have copied some nice picture of a surface or thin film. Unfortunately, I didn't have time for that. Okay, so I was just lazy to do that. But basically, we are dealing with layered systems. That means our system is composed of layers which are shifted with respect to each other. This shift is reflected in these layer generating vectors, and the two-dimensional translation periodicity, which is valid for all the layers, is represented by the 2D lattice vectors. We have here two basis vectors or primitive, no, not basis vectors, these are the primitive translation vectors in 2 dimension, and so the lattice positions can be written like this. Here, actually, I can just tell you that that this P index can denote just atomic layers, but for complex lattices, where in one atomic layer you have inequivalent size, that means sublattices, then this P can even denote sublattices. So, but here I just deal with the simplest case, where we have a simple lattice, that is 1 atom per geometric layer, and then these, in case of or without layer relaxation, better to say without layer relaxation, this is just a multiple of a C-naught vector. But there is no problem at all with treating layer relaxations. So we have a set of CP vectors, and usually in this setup we use the layers denoted by negative numbers correspond to a semi-infinite bulk, where we suppose that the surface or interface or multilayer or whatsoever have no effect to the potentials. So in this part of the system, all the layers are equivalent, just shifted with respect to each other, of course. Then we have an interface or interface region, I would say, a central region of the system, which contains the surface interface or a slab or a multilayer. So this is the region which is composed by capital N layers, contains the layers which we want to deal self-consistently. And from the right, again, we have a semi-infinite system characterized by the same potentials, and therefore it can be, for a case of an interface, it can be a semi-infinite bulk, or in case of a vacuum, we artificially cast the space into cells, also on the vacuum side, and then we have a kind of empty cells or layers composed by empty cells. So this is how we take into account the vacuum, and also then we suppose that about depends on the system, of course, 4, 5, 3, 4, 5, 6 or whatever layers far from the surface, there is not anymore change in the vacuum potential, and therefore it is a semi-infinite, ideal semi-infinite system again. And this is actually what was the strict idea of Peter Weinberger at that time. So I introduced him already. So he was the professor in Vienna. Okay, from the second slide you probably remember, who invited us with Balázs about 30 years ago to program a surface code and to perform surface calculations. I will speak a little bit later on what kind of calculations I'm thinking on, and then our very basic assumption was that we want to deal a system like this. So we didn't want to deal a supercell formalism where, of course, you can have it under control, but basically you can have artificial effect of repeating supercells or any other kind of treatment of surfaces. We wanted to have such a system, a kind of more or less exact description of the layered systems. I will come back to this point later on. And now, what about this, the previously mentioned structure constants here. Basically similar to the three-dimensional case, we can do a two-dimensional lattice Fourier transform, for which this series of papers by Campbell provide sufficient basis. It is not easy to program. For us, it was Arthur Ernst who programmed these structure constants. So, of course, here the Ewald summation is much more complicated than in three dimension, but it is possible to get closed forms for these quantities and then to program them. And here I have to emphasize, at this point I have to emphasize again that those papers deal with the case when the CP vectors are inhomogeneous. That means layer relaxation. So once one programs or codes the Campbell structure constants correctly, then one can deal with layer relaxations. All right, so we are not restricted to this approach at all. Right, but of course in that case, because the system is inhomogeneous, at least in this part, in the interface part, let me call it like that, in the interface part, the potentials are changing from layer to layer. Therefore, at best, we can introduce layer-dependent T matrices, which are, of course, again diagonal in the layer indices. We have these two-dimensional case-based structure constants. And then, similar to the three-dimensional case, we get the two matrices in case we can perform this integration. I just have to check time. Okay, so it will be easily 1.5. I will cut the applications then. All right. So the problem here is that these matrices are infinite in layer indices, and as I mentioned right at the beginning, that the structure constants are long range. So what to do actually if we insist on performing this inversion? That was actually the basic question for us at that time, and then we found the solution in the so-called Screened KKR, where which as a preliminary we were working together in Peter's group with our Czech colleagues, and they used it already at that time, the so-called tie-binding LMTO, where they actually had a kind of auxiliary Green's function which was exponentially decaying in real space. So they already used a kind of screening, but it was not clear how it works in this multiple scattering, and this was actually which was advised and which we learned from Peter Dederick's, if I'm right, Balázs.
Absolutely.
All right, and now without too much historical comments, I want to introduce these theories. So basically, what we do, that we change the reference system from the free space to another space to another reference system, which is described by the potential VR. So now I'm just speaking first two slides about the general formalism, and then I go what actually screening means. So we are now just introduce a new reference system characterized by the potential VR and correspondingly by the T matrices TR, and then we can construct the previously introduced structural Green's function matrix of the reference system labeled by R by using the same equations we had before. And then we introduce the T matrix with respect to the reference. And this is T minus TR. That's right. And then we want to express the SGF matrix of the system under consideration in terms of the so-called screened structure constants. And right now we don't know why it is good for, or what it is good for, but the mathematical problem is quite clear. That please try to express G in terms of GR. Here there are some matrix algebra which is based that we want to separate GR, this quantity, in this inversion. So now because I see that time is flying quite fast, so I don't want to repeat all the steps, but actually we get a very similar equation like this, but instead of G naught we have G of R, and instead of T, the T matrix, we have the T matrix with respect to the reference system. So it is a quite natural result what we have here. And the nice point here is that we can compare the previously known expansion of the SGF matrix with the new expansion, and actually we just say that this kind of screening transformation, the essence of the screening transformation is that it lets the structural Green's function matrix invariant, no matter what is the reference system. So this is the basis of I would say, of the theory, sorry. Just you have to define the relative T matrix correctly. The only problem we had that we liked the scattering path operator formalism of multiple scattering, and therefore we wanted to introduce the so-called screened SPO or scattering path operator matrix, which from this manipulation you can easily see that it is meaningful to introduce this quantity as the screened scattering path operator. And again, the big advantage of this definition is that here we have the Green's function matrix, or structural Green's function matrix of the reference system, what we call a screened structure constants, and if it has convenient properties, then it facilitates the calculation of the screened scattering path operator. Just you will see in the next slide, and then from this expression, what I show here, I hope that you can see the cursor and the expression I'm pointing with the cursor, that the TS is related to G like this, but the TS, the screened scattering path operator, is something else. So usually we say that it's an unphysical tau matrix. So it has actually no direct relationship to the Green's function. So we have to calculate the physical tau matrix. And from these two equations, so again, the main point is that the G here is the same. That's the invariance of this transformation, invariance property of this transformation. From these two equations, we can more or less easily express the tau matrix in terms of the screened SPO matrix. And this looks very complicated, but for that reason I wrote it out in terms of site indices. You can see that once you have the screened SPO matrix, so you can if you are able to perform to carry out this inversion, then you get the physical tau matrix, the blocks, matrix blocks of the physical tau matrix in terms of side diagonal matrix multiplications. So this looks complicated, but it is easy to perform, easy to calculate. So the main question is how whether this equation helps us in case of the two-dimensional layered systems or layered systems with two-dimensional invariance. And again, my good old friends, Rudy Zeller and Peter Dedericks worked out, okay, I hope that we added also something to the theory and to the calculations. Of course, we published this paper almost more than 25 years ago, I should say. And the main idea is that, and this is what explains why we call that screening transformation, because in that case, at least, probably this is a more general expression in physics, but in our case, the main point is that we should use the reference potential such that it screens out, it removes the continuous spectrum of the reference system from the energy region we are interested in, from the relevant energy region. This means that in the reference in the energy in this energy region, if this happens, then GR will decay exponentially in real space. And this is a very sloppy explanation for that, is that if the energy, and this is if this V of R, not V of R, VR is larger, is sufficiently larger than the energy, than the Fermi energy. So in case if we like to perform self-consistent calculations, then we could say that it should be sufficiently larger than the highest occupied energy, that means the Fermi energy. Then for this case, as I started in my talk, the Green's function is exponentially decaying. And then, of course, if we expand this Green's function in terms of Bessel functions, then the structure, the corresponding structure of Green's function matrix or structure constant is also exponentially decaying. And actually, Rudy showed that practically this energy difference shouldn't be much large. It can be 1 Rydberg or so. Usually, we use 2 or 3 Rydbergs above the Fermi level for this atomic potential, for this potential. Of course, in the construction used by the multiple scattering, we always have atomic potentials. Of course, the reference system is characterized by atomic potentials, and these atomic potentials should be repulsive, composed by repulsive potential wells characterized by V of R. An additional comment is that usually the screening potentials are spherical, at least in our implementation. These are spherical, and therefore they are diagonal in the momentum space. This will have some consequence to an easy formulation of the relativistic screened structure constants. Please remember, and then Rudy's calculations showed that, for example, so this is a picture, or no, a table from this paper, that in case of copper, if you choose VR 2 Rydberg, 4 Rydberg, 8 Rydberg, whereas the Fermi level was about, as I can remember, 0.6 Rydberg, then the bottom energy of the continuum band, below which there are no states of the reference system, are those values. This doesn't grows linearly with V of R, so it saturates actually, but it's absolutely enough for sufficient for us, for our purposes, that in a range up to 0.5 Rydberg, where our occupied states are, the corresponding structure constants, or GR is exponentially decaying, and this was shown in this paper among many other features of the screened structure constants, where a kind of partial norm here is the norm. This normalization, I cannot exactly remember why we choose that, so please ask Balázs, or Rudy is online, I believe. Okay, so but you can ask him. So why we choose that? I have some idea, but I don't want to puzzle now. But the main point is that it is a kind of norm, matrix norm, corresponding to LL prime, to the LL prime block of the screened structure constants, and you can see very nicely in case now for the L equal L prime cases, I think L equal 0, 1, 2, 3, 4, that it is exponentially decaying. Very nice. Whereas G naught, the same quantities for the free space structure constants are not exponential, are long range, as I said. And this is the point. And this gives us the idea that if screening is successful, then we can from a given distance we can neglect the screen structure constants, and this is usually some atomic distances where we can do that. Of course, it is very much structure dependent, so dependent on the geometrical structure, and this is actually which reminds us to the die-binding schemes. And therefore, I think there was a time, or still, if they speak about, then Jülich people call this Screened KKR as tie-binding KKR. Okay, we tried. That's okay. So this is the proof of the concept. And now back to the layered formalism. That we can of course perform or calculate the lattice Fourier transform of the screen structure constants. I will elaborate one slide how usually we do that, and then the question is how to calculate these two-dimensional lattice Fourier transform. So either you use this equation, and again here I showed in details, but I don't want to explain it now because it's elementary solid-state physics. That again we can say that this kind of fundamental equation factorizes to k parallel points, and basically defining now the supermatrices in terms of layer indices. I didn't want to use, I couldn't use actually different labels like these boldface labels, but now we have no site indices. Instead of site indices, we have layer indices. Fine. Then we can formulate this equation like this, very similarly like this, but for every k vector, and then the Fourier transform of the screen structure constants can be calculated by using the same kind of equation as we have seen before on the third or fourth slide. That's right, and this is actually what the Vienna Budapest code uses. We calculate the Campbell structure constants by analytic formulas, and then perform this matrix operation. And since G of R, GR is exponentially decaying in the layer indices, this is a kind of one-dimensional problem actually. So in layer indices, then one can easily prove that this matrix inversion can be performed confined to a not too large portion of the one-dimensional chain. So it's doable. It's doable, and then what we make use in the code that in terms of layer indices, once we perform this matrix inversion, basically, then we can truncate the couplings between layers, and usually this is the control parameter of the two-dimensional formalism, which for simple lattices probably, I have one more line here. So for simple FCC BCC lattices, it is m equals 3. For more complex lattices, or in case of layer relaxations whatsoever, it can go up to very large numbers. But this is for topological semiconductor or insulators or whatsoever. So for hematite or whatsoever. So these large numbers are actually arise because of the large units of the system. Usually it is below 10. This cut parameter, and then we will see what it is good for. But before I briefly discuss the strategies to calculate the screen structure constants, so how to perform these matrix or how to solve this matrix equation. You can, of course, do that in real space. This is nice. Probably you need quite large clusters, not for FCC or BCC. So as I know, some dozens of atoms are sufficient for the FCC BCC clusters, but structures. But for more complicated systems or geometries, you should use quite large clusters, no matter. But the big advantage is that then you have the screening for a given energy, and then if you do that for a given energy, sorry, I dropped here the energy argument, for a given energy, then in terms of a Fourier transform, you can calculate any thousands or 10,000s or 100,000s of K parallel points. So this is definitely a big advantage of this method. What we, as I said, what we use is the implementation in 2D K-space. I explained on the first slide, where the very time-consuming part of the calculation is that you have to do the screening transformation for every K vector. Probably I can go back here. So I'm speaking about this equation. And this is very inconvenient for magnetic and isotopic calculations, where you should use sometimes many thousand or even 10,000 of K points. All right. A small benefit is that the screening transformation have to be performed for smaller matrices, because we are in layer space. I mean, we are working with the layer indices and not site indices. All right, and actually the exact treatment is the third version, which we used for several years, because at that time in the 90s we haven't considered layer relaxations, and then we got many criticism from our colleagues, and then we had to, of course, include layer relaxations in our calculations. But at that time, if you have no layer relaxation, you have a perfect bar system, then actually you can start with this three-dimensional K space formalism. You can perform this screening transformation in three-dimensional K space formalism, where these matrices are very small. I mean, very small. Come on, so they correspond to angular momentum indices just. And in case of a simple FCC BCC lattice or whatsoever, you have no site index in this matrix inversion. So therefore you can perform this screening transformation basically exactly, apart the angular momentum cutoff, of course, and then you just integrate back with respect to the k component normal to the planes, and then you get the two-dimensional k-space screen structure constants. So this is what we used, as I said, for about 10 years and produced quite some nice papers, I hope at least. Fine. And then I think, because time is going away, I don't want to go too much into the relativistic screen structure constant. That is, the whole theory applies for the relativistic case, where you know that the structure constants. I hope that either from Hubert or from Julie, you have heard that the structure constants. Now A and B are the site indices. We have so many indices, LJ, M, and so on, that I didn't want to use the IJ or NM indices for the site. So AB on these slides and the next slides are site indices. So the non-relativistic structure constants and the relativistic structure constants are related to each other in terms of a kind of matrix transformation in terms of the Clebsch-Gordon coefficients, and this is valid for flat screening potentials. So even in the relativistic case, we can deal with the non-relativistic screening potentials if we have a rectangular potential well, and then if doing so, then you can look at all the terms here, but actually it is enough just to prove for the second term, which you can see here. I'm sorry, I'm now a little bit running. That if you calculate this product of matrices for the relativistic structure constants and T matrices, and you make use that this is still this still depends just on the L quantum number, and you use the transformation of for the relativistic free space structure constants, then you end up with the result that this term is again just the non-relativistic term. So these are non-relativistic matrices blown up. Sorry to formulate like this, by the Clebsch-Gordon coefficients. I just so blow up means just that the J mu indices are doubled in this in space, then or double dimension, have double dimension as compared to L and M. Anyway, LMS has the same dimension as JMU. Right. Then we have the final result that just as the free space structure constants, the screen structure constants transform in the similar way from the non-relativistic to the relativistic one. Then this means that we don't have to perform the screening transformation for the structure constants for the relativistic structure constants. It is enough for the non-relativistic ones, and then just use the Clebsch-Gordon coefficients to get the relativistic quantities. Fine. And now I'm coming to the technical, to the end of my technical talk, and probably I will have time to show one application. That why is this formulas good for to facilitate surface interface calculations? We have to look at the structure of the GR matrix, and once we use this truncation, for example, in that case m equal to what I introduced before, then the structure of the screen structure constant, the matrix structure, looks like that. All blocks correspond to an angular momentum block of the screen structure constants, and these denote the sides. So these numbers denote the sides. And because of m equal 2 in a line and also in a column, so in a row and in a column, there cannot be more than 5 blocks. Because if the P and Q indices differ from each other more than 2, so then they vanish because of the truncation, we suppose. So in that case, the minus 2, 1 block is 0 because it's an exponentially decay. So I hope that this is probably clear for all of you why we do have these matrix structure of the GR matrices, and then we have the idea that we can decompose we can regroup. Sorry, just vice versa. We can regroup the structure constants into 3 times 3 blocks like this. So this rounded or framed by double lines. So these are the blocks, matrix blocks framed by double lines. If you do that, then you recognize that there is a coupling between these double line rounded blocks. There's a coupling only between the neighbor blocks. And this is why we call this group of layers as a principal layer. So in that case, 3 layers compose one principal layer, and then you can write this. You can partition the screen structure constants. Here, okay. Sorry for this spelling error. In principal layers, such that here the principal layers are, again, they contain or they comprise 3 atomic layers, and they couple just between the adjacent principal layers. So this that means this matrix has a block tridiagonal form, like in a one-dimensional nearest neighbor tie-binding scheme. So this matrix has a very simple structure, and then you can perform or you can calculate the scattering path operator matrix in the so-called interface region I was speaking about quite easily, because roughly speaking, the equation you have to solve is like this, or looks like this. Sorry, here I should have written the corresponding tau matrices, because I just state from this matrix, which is the inverse KKR matrix, because of this previously discussed structure of the screen structure constants, that this has this matrix has this form. So this is the interface block. This is the left, and this is the right block, and so on and so forth. And here, these are actually not 0, but I'm interested, or we are interested, just in the interface, in the projection of the scattering path operator matrix in the interface region. And this is a well-known, how to calculate tau II is a well-known problem, solved problem in linear algebra. So here I put down apart this error actually, but these equations are right, and also this expression is okay. So we can find this expression in any of any linear algebra book. Fine. And then the only question is how to calculate these two terms, because these tests, if I neglect these two terms, then actually this means that I consider just the scattering events in the interface region. And these two terms actually ensure that all the scattering events in the left and right semi-infinite regions are taken into account. And here just remember the structure of these matrices, because there is only one, here I write it, because of the block diagonal form of these matrices, there is only one block which connects these left and right region or part of the matrix to the intermediate or interface part. And actually the final equation is this. And here you can see that all you have to do is to calculate the left upper or right most bottom block of a semi-infinite, perfect semi-infinite matrix. Here I don't have time to go into details, but these matrices are actually, which are called the surface Green's functions in the tie-binding LMTO formalism. In our formalism, those can be called as surface scattering path operator matrices, and these can be done by using a decimation technique, which can be found, for example, in this paper. So this is actually sometimes a very time-consuming part of the calculation to find these surface, these blocks of the semi-infinite, perfect semi-infinite or ideal semi-infinite matrices, or the inverse of these ideal semi-infinite matrices. But this is a very efficient method and works almost always. It is an iterative technique actually. So here actually I stop with the technicalities. I think that was far enough for you and also for me, because I just wanted to show that it is possible. There is a machinery how to calculate exactly, probably in parentheses, exactly the scattering path operator in the interface region. And from that, again, this is what we do for each of the energy and K points. Then we can integrate it in the Brillouin zone. Then we get the real space to matrices from which we can calculate again density of states, charges, densities, and moments, and so on, and perform self-consistent calculations for any kind of almost any kind of surfaces and interfaces. That's okay, and I also introduced that these calculations can easily be expanded into in the relativistic formalism. So we can do relativistic spin-polarized calculations, and then depending on the T matrix of the treatment of the scattering, you can even include correlations and so on. So from this point, we have an ordinary KKR method. So nothing is screened KKR specific. And Balázs will speak about one of the latest development we did, that to solve the Bogolyov-Lejeune equations for superconductors. This is also possible. Fine. And here I just summarize some properties of the Screened KKR code we have, which is now a Budapest code. Unfortunately, the collaboration with Vienna, effectively the Vienna group doesn't exist anymore, at least the KKR group. So therefore, now it is treated. This code is treated and maintained in Budapest. And as I already so I was speaking about these points, which ensures that at At least in terms of the principal layers, it is an order n method. Unfortunately, if the principal layer is large, then in size of the principal layer, it is so it is not that convenient. So it is order n cube, and this is for the different treatment of the T matrices actually. So all what we have, so we have quite some extension of the code. So this is okay. I advertised already this talk, and then we have some related codes on top of the self-consistent calculations we do. For many years, we have done a lot of transport calculations, even magneto-optics calculations in terms of the Greenwood-Kubo formula. Unfortunately, not in the latest 10 years, because we much rather turn to describe and study magnetic surface magnetic system or clusters, magnetic clusters. So nanomagnetism in general, and for this we wanted to calculate spin model parameters, which we do in terms of the relativistic torque method or the spin cluster expansion method. Unfortunately, I will not speak about this, but interested people should ask Hubert or Sergei Mankovsky what those methods are good for, but they facilitate the study of zero temperature and even final temperature magnetism. And we have on top of our Screened KKR code an embedded cluster code for which we can perform calculations for clusters embedded in bulk or on top of surfaces, and ab initio spin dynamics is also included, in particular for t equals 0, so we can look for the magnetic ground state of systems with complex magnetic structure. Partially, we can, so there were some trial calculations that we can do non-zero temperatures, so final temperature ab initio spin dynamics. But here we have to work much more to test the code. So I think time is over. So let me tell just the very first application, which was actually the main motivation of our calculate of this development. This was the magnetic anisotropy of thin films. In particular, our very first calculation was for iron layers on gold 001, and probably what you should know about magnetic anisotropy, that basically it comes from two effects. One is the electronic structure effect controlled by the spin orbit coupling, which we calculate in terms of energy differences, specifically in case of when using magnetic force theorem, then there's a difference of the band energies, and the other is the magnetic dipole-dipole interaction. Yesterday, Julie was speaking about that, and the magnetic anisotropy is the sum of these two energies. And the last slide I can show you is our very first results by using this Screened KKR code for the relativistic spin polarized formalism, where you can see the results as a number of iron layers on top of the gold surface, and you can see that the spin orbit coupling part, so or the anisotropy which comes from the spin orbit coupling is practically constant, so not much changing, and it prefers the out of plane orientation is positive, whereas the dipole always prefers the in plane orientation, and the sum of them crosses zero, and this is a kind of spin orientation transition, and this is probably why this is still one of our best cited paper. So thank you so much, and sorry for talking so long about the technicalities. I'm sorry for not being able to speak about more applications. Just the last slide is replacing the summary that of course Screened KKR can be used for systems with no translation invariance, and these are clusters with for any kind of structure, and this is maintained by Rudy and in Jülich, and they perform very nice calculations, for example, lately for magnetic skirmions or skirmion structures, skirmion bubbles, and so on and so forth. So, but I had time just to speak about the layered formalism, and thank you very much for your attention. I'm finished, thank you.
Thanks, László, for this nice talk. So, questions?
Just come back to the Zoom.
Yeah, just could you come? Sorry, we have to organize it here always. The people are coming down because the microphone is not so good of the computer. So, yeah, no, come here. I can see. He can see you.
Okay, so I just have a simple question that I know that in this Screened KKR, the structure constant becomes localized, and then you can just, the matrix becomes block tridiagonal. But my question is that how you calculate the Hartree potential, because in this layer system, in 2 dimensions, there are 2 dimensions. They are periodic. I can use somehow like the Ewald summation technique to calculate the Hartree potential in these 2 directions. But in the 3rd direction, which is not periodic, how you treat this? How you calculate these Hartree potentials? Because the Coulomb potential is somehow proportional to 1/r, which is non-range. Thanks.
Yeah, so if I understand correctly, the Hartree potential is the electrostatic potential, and for this we use a similar Ewald summation as for the.
But as far as I know, the problem is that in the 3rd direction, the structure is not periodic.
Okay. So your problem is that what we do in the 3rd dimension. That's actually our systems. What we deal with is, as I said, those are semi-infinite. So these are bounded or surrounded between or sandwiched between 2 semi-infinite ideal systems, and we suppose that in these ideal systems we have the total charge is 0. So basically we deal with systems where you have contribution to the Hartree potentials only from a finite number of layers.
Just as a comment, so we want to see it explicitly in the book which László and his colleague wrote. They have a nice chapter on how to solve the problem, how to put a proper boundary condition if you have on the one side vacuum, on the other side semi-infinite bulk, and so on.
Okay, I will check that.
Just as
okay, thanks.
Some other questions? Yeah, Didier.
Hi, László. Just a short question. I was wondering if you ever tried to use it to model spectroscopies at, let's say, substantial energy, because in that case I would expect, I guess, your matrix elements, your structure constant to fall down more quickly. No?
So you, if I understand, the problem is if you want to deal with energies, the states with energies above the Fermi level,
Yes,
or
exactly.
far above
Yes.
the Fermi level.
Yeah.
So I do not have too much experience with that. From my talk actually, and from the experience I have, probably Rudy can confirm this. As even for hard sphere screening, so using infinitely large potential wells, the bottom of the band doesn't go up very high, so it has a saturation, which I don't know exactly how much is it, but probably it is not more than about 5 or 10 Rydberg. I never checked it. Therefore, I guess that, or at present, I would say that for this kind of spectroscopical applications where you need energies much above the Fermi level, at least in that form, screened KKR cannot be used.
Okay.
So what
At least these tricks of the screened KKR cannot be used, so you cannot localize the Green's function.
Okay. Thanks.
Okay. Some other questions? Ondra, you had one. You had to ask one.
Actually, it is related to what Didier spoke about. I just wonder whether there is a principal reason why not use this reference potential as, let me say, 40 Rydbergs or 400 Rydbergs. I understand that you would get the bottom of the conduction band would, let me say, be shifted up. That there's a saturation, fine, but at least I would know that I am getting as much of it as possible. So I guess there may be some technical reason why not using 400 Rydbergs reference potential, but I just wonder what are these reasons, if they are.
László, your microphone is off.
Yeah, I interrupted, my connection interrupted a bit. Okay, so, okay, fine. So we use even more than 400, we use even hard sphere screening. So where you have infinitely large potential, this is just a tutorial job for bachelor students to calculate the scattering matrices for hard sphere potentials. But telling the truth, I never checked what is the value, what is the saturated value of this band bottom. So now I don't want to puzzle. I don't know whether Rudy is still with us. At least I can see him. At least his name. But this is all I can tell right now.
Yeah, he has to say something. If he can. Rudy?
Yes?
No. Yeah.
Do you hear me?
Yes.
now it's fine.
At least me. I can hear you.
Yeah, so even if you do a hard sphere, an infinite repulsive potential, you will saturate, say, a few Rydbergs above the Fermi energy. I don't know, remember, but I think you cannot go much more than 2 Rydberg above the Fermi level with the Screened KKR formalism.
So I thought that probably a bit higher, but definitely not too high.
It makes no sense to go from say 10 to a million Rydberg repulsive potentials. You get not much difference.
Okay,
And
thanks.
this is because space filling of the repulsive potentials is only a part of all space. And so the electron waves can't tunnel between the repulsive potentials in the region where there is no repulsive potential. Because the repulsive potential is confined to the muffin-tin spheres. And there's no repulsive potential in between, in the interstitial region.
May I ask? I know that actually already Balázs should start his talk, but probably a very last question that if you use full potential and full potential screening, that means really space filling repulsive potentials, then in fact you can go up with the.
Yes, if you use full potential, repulsive potentials, you can go up. I checked it some years ago, but there was a problem that also ghost states somehow appeared, and since I was always only interested in investigate what was really happening.
Okay.
But with full potential repulsive systems, you can go higher.
Yeah.
Okay, thanks. So I have to stop it now here because we have to go for the next session. So thanks a lot, László. Thanks also, Rudy, for joining us.
You're running off time.
And
thank you.
Have a nice evening.
Yeah.
Bye. Thanks.
At your work. All right. Thanks. Sorry, I have to leave.